So I want you to imagine standing at the entrance of a an impossibly complex maze.
Okay, like a huge labyrinth type of thing.
Yeah, exactly. If you want to find the exact route to the exit using a normal supercomputer, it basically has to act like a person running through the maze completely blindfolded.
Oh man, just hitting dead ends and starting over.
Right. It runs through every single path, one by one. It hits a dead end, turns all the way around, resets, and just tries the next path. It's a process that, for a truly complex maze, could take thousands of years.
Which is obviously not ideal.
No, not at all. But what if you had a completely different kind of machine? Something that could just, hover above the maze, look at every single path simultaneously, and instantly highlight the correct route out.
I mean, that honestly sounds like science fiction.
It does, right. But this isn't science fiction at all. This is the exact promise of quantum computing. We're talking about a technology that operates on the completely bizarre hidden rules of the subatomic universe.
It's just wild to think about. It really is. Welcome to the Missing Lessons, where we explain what school never did. Today, we're doing a deep dive into the ultimate shortcut to solving the universe's biggest problems.
We're basically going to unpack how these machines actually work, right?
Exactly. We'll explore why they hold the key to curing diseases and stopping climate change, and on the flip side, why they simultaneously pose a massive threat to global security.
Yeah, it's a pretty heavy topic, but so fascinating.
Really fascinating. Real quick, if you're enjoying the Missing Lessons, make sure to follow the podcast, leave a rating, and share it with someone who might find it interesting. It helps us create more episodes and reach more curious minds.
Okay, so to even begin understanding this crazy maze-solving power, we essentially have to unlearn everything we know about normal computers, right?
Pretty much, yeah. So classical computers, and I mean everything from your smartphone to the world's current fastest supercomputers, they all run on binary bits.
So just the standard zeros and ones.
Right. Everything is a 0 or a 1. It's kind of like a solo voice singing one single note at a time. So what makes a computer quantum then?
Well, it introduces this thing called the qubit, or quantum bit. Instead of just being a 0 or a 1, a qubit exists in this state called superposition.
Superposition. Okay, what does that actually mean?
It means it can be a 0, a 1, or literally any combination of both at the exact same time.
Wait, really? At the same time?
Yeah. So if a classical computer is that solo voice we talked about, a quantum computer is like a massive symphony with, many tones interacting all at once.
Wow.
And the scaling is where it gets truly insane. Like 2 qubits give you 4 combinations simultaneously, 3 give you 8.
It just builds on itself exponentially.
Exactly. By the time you reach just 100 qubits, the number of possibilities you can explore at once is astronomically huge.
Have you ever felt completely paralyzed by having too many options to process at once? That's exactly how classical computers feel when trying to solve the real world's most complex problems.
That's a perfect way to put it. But having millions of possibilities happening at once is useless if the result is just random noise,
Wait, yeah, if they are all entangled and existing in multiple states at once, how do we get a single useful answer without it being completely random?
So the computer actually uses 2 more really bizarre rules of quantum mechanics. The first one is entanglement.
Entanglement, that sounds like a messy relationship.
Kind of, yeah. Basically, qubits can be linked together so perfectly that measuring the state of one instantly tells you the state of the other, no matter how far apart they physically are.
That is just spooky. But how does that give us the right answer?
That brings us to the second rule, which is interference. The computer uses probabilities that basically act like waves.
Like ocean waves or sound waves.
More like sound waves, actually. When the quantum algorithm runs, the waves of the correct answers amplify each other.
Okay, so they build up and get stronger.
Right. And meanwhile, the waves of the incorrect answers crash into each other and just cancel out.
Oh, that makes sense.
Yeah, it's exactly like how noise-canceling headphones block out unwanted sound on an airplane. You don't have to listen to every sound. The headphones just cancel out the garbage.
So the computer just cancels out all the wrong paths in the maze. That's brilliant.
It is, but, because these qubits are operating on this delicate subatomic level, they are incredibly sensitive.
Right, I'd imagine the very traits that make them so powerful also make them incredibly fragile.
Exactly. I mean, these machines don't look like sleek laptops. When you see a picture of them, they look like these massive, glowing, golden chandeliers.
Yeah, made of all these complex tubes and wires, right?
Yep, and they're suspended inside these giant vacuum chambers because the fatal flaw of current quantum tech is something called decoherence.
Decoherence. So they just fall apart.
Basically. If a qubit is exposed to even the slightest vibration, or a stray particle, or even a tiny shift in temperature, its quantum state completely collapses.
And then the whole calculation just fails.
Right. I mean, the current error rate is roughly 1 in 1,000.
Oh, wow. That sounds pretty high.
It is, especially when you compare it to a normal computer, which has an error rate of about 1 in a billion billion.
That's a massive difference. So how do they stop this decoherence from happening?
Extreme engineering. The core of the quantum computer actually has to be cooled using superfluids down to a fraction of a degree above absolute zero.
Wait, absolute zero.
Yeah, we're talking negative 460 degrees Fahrenheit or negative 273 degrees Celsius.
That is insane.
I know. Would you have ever guessed that the most advanced technology on Earth requires an environment colder than the vacuum of deep space just to function?
Definitely not. But I guess that brings us to the real question. Why go through all this extreme engineering? What does this actually mean for everyday people, workers, and businesses?
Well, the payoff for society and the economy is almost unimaginable. Let's look at medicine and chemistry, for example.
Right, because right now discovering drugs is a super long process.
It really is. Instead of scientists using slow trial and error to mix chemicals in a lab for years, a quantum computer can just perfectly simulate molecular behavior.
Because molecules already operate on a quantum level anyway.
Exactly. So this means we could discover new life-saving pharmaceutical drugs in a fraction of the time.
That would change everything. What about for businesses?
It's just as huge. Imagine simulating and optimizing traffic flows for millions of cars simultaneously, or routing global shipping lanes instantly.
Which would save businesses, what, billions of dollars?
Easily billions. But we do have to talk about the dark side of this, too.
Right, there's always a catch, the security threat.
Yeah. Quantum computers could easily solve the complex math problems that our current encryption relies on.
Like the standard encryption we use right now.
Yeah, like the 2048-bit RSA standard.
Oh.
So they could theoretically crack the passwords protecting global bank accounts and private data.
Okay, wait, should we be emptying our bank accounts right now?
No, don't panic. You don't need to stash cash under your mattress just yet.
Okay, good to know. But why not?
Because something called post-quantum cryptography is already being heavily researched and developed.
So they're creating new locks before the new keys get made.
Exactly. They are working hard to protect us before these machines actually reach that level of code-breaking power.
That's a relief. But, looking at a technology that could save the world, it kind of comes with this massive, ironic cost.
You're talking about the environmental paradox. Yeah, I mean, keeping these machines at absolute zero requires a massive amount of electricity, specialized cooling hardware, and resources. They are definitely not naturally green machines. That's completely true. They use a ton of energy. But you have to counter that with the big picture.
Meaning the solutions they provide might balance it out.
More than balance it out. While running them is super energy intensive, the solutions they provide could completely revolutionize sustainability.
Like what kind of solutions?
Well, they could model much better flood and wildfire predictions. Or they could discover new materials for highly efficient batteries.
Oh, or even create things like green ammonia for clean energy.
Exactly. So the question becomes a real debate.
Yeah. Which explanation do you find most convincing? Do the long-term environmental benefits of quantum problem solving outweigh the massive immediate energy costs of running these machines?
It's honestly a tough call, and it's something we'll all have to reckon with soon.
Speaking of reckoning with things, here's a question for you. If quantum computers could perfectly simulate nature and solve our biggest global crises like disease and climate change, but it meant completely destroying and rebuilding all of our current digital privacy in the process, would that trade-off be worth it? Let us know your thoughts in the comments.
That is a fantastic question. To sum up everything we've talked about today, we are currently in this massive transition phase.
Right, moving away from the old binary world.
Exactly. We are leaving the world of just zeros and ones and entering an era where we actually harness the strange, multidimensional rules of the quantum realm.
Even though we're still dealing with those high error rates you mentioned earlier.
True, the error rates are a hurdle. But we are rapidly moving from what experts call quantum utility, where these machines are just useful research tools,
to quantum advantage.
yes, quantum advantage. That's the point where they completely outperform classical supercomputers.
And that's expected to drive a $1 trillion industry by 2035.
$1 trillion, yeah. It's going to reshape everything. But before we wrap up, I want to leave you with one final kind of profound thought to mull over.
Okay, let's hear it.
Quantum computing is actually often described as the most natural form of computing.
Natural, even with all the giant vacuum chambers and freezing temperatures.
Yeah, because think about it. The real world operates on quantum mechanics at the subatomic level. So when we build a quantum computer, we aren't just building a faster calculator.
We're building something that actually speaks nature's language.
Exactly. We are literally building a tiny synthetic universe inside a box, one that perfectly mirrors nature, so we can finally ask the universe for its deepest secrets.
That is incredible. If you enjoyed this episode of The Missing Lessons, don't forget to follow the podcast, leave a rating, and share it with a friend. Your support helps us continue exploring the topics school never taught us.